And I'd like to start the lecture now, please. Hello again. I want to start by reminding you, that you have some homework due. So let me just make sure that everyone has seen my announcement. I asked you to work on homework number 3, and it's going to be collected on Wednesday. Okay? And now let me remind you what I was doing before reading week. So here it is. Remember, we are trying to find prices of derivatives, and we said if we live in a very simple world in which underlying asset prices go up or down at each period of time, we know how to deal with that. But then we said, let's look at what happens in the real world. We need to have a model of evolution of prices in the real world. And then I said, when we look at prices, they jiggle up and down. We're going to use something in mathematics which is also used to model the jiggling up and down of other things. And then I said, let's have a look at Brownian motion. So I showed you videos of particles following Brownian motion. They jiggle up and down. And we said, that's going to be what's going to drive the jiggling up and down of underlying asset prices. And so we introduced Brownian motion. We ask ourselves first, what sort of random variable S of t is going to be the random variable describing the price of something at some point t in the future. And then I said, well, the main building block is going to be this thing that jiggles up and down, Brownian motion. So we said, let's define what Brownian motion is. I gave you the mathematical definition of Brownian motion. So we looked at a stochastic process that is a family of random variables indexed by time. So this family of random variables is defined on some probability space, which is very mysterious to us, but it's there somewhere. And we said, what is the thing that we're going to call Brownian motion? So we want this stochastic process defined on this probability space, so whose properties is that B of 0, the random variable corresponding to time 0, is identically equal to 0. And then we look at the increments from one time to another. Then the increments are going to be normally distributed with mean 0 and variance t minus s, that is the length of the time period over which this increment of time is happening. And then if we take a period of time and we chop it into non-overlapping time intervals, then the increments of the Brownian motion over these non-overlapping increments, non-overlapping intervals, all these increases are independent. And finally, we want our particles following Brownian motion to have a continuous path. So we say, if we fix the world we're observing, which amounts to fixing a little omega in big omega, in the sample space big omega. And if we now look at what happens at various t's to this particle following Brownian motion in this world we just chose, what we're going to get is a continuous path. So the function that takes t to b of t for a fixed omega is continuous. So this was our mathematical definition of Brownian motion, and then we said we're going to be using this to construct other more complicated things, which brought us first to some nice pictures. So here are 3 instances of Brownian motion, which correspond to living in 3 different universes. So I chose this universe, and this universe, and this universe, which we don't know beforehand in which universe we're going to find ourselves. So we took 3 universes and we described the motion of a particle following one-dimensional Brownian motion in each one of these 3 universes. And then we saw that, well, I told you that Brownian motion exists, there is such a thing, it has some strange properties. For example, this continuous paths of particles is continuous, but it's differentiable nowhere. So there is no well-defined velocity to particles following Brownian motion, which is very strange. So I hope you remember the strangeness of that. But then we said we're going to take Brownian motion, we're going to use it to construct something else. So we start with this family, the stochastic process, which is Brownian motion. We want to construct new families of stochastic processes. And the way we did it is by defining the Ito integral. So what is the Ito integral? So I'm going to give you the bottom line instead of taking you through the construction. You come to me and you say, I want a stochastic process X. So what do we mean when you say stochastic process X? You're saying, I want the family of random variables indexed by time. So for every t greater or equal to 0, you want to have a random variable xt. And you want that this stochastic process has the property that when you look at the increment in the value of this process x, so if you look at the value of x now and you compare it to the value of x after an infinitesimal period of time dt, the way it increases, the change in the value of x, has two components. One of them is going to be proportional to the length of this infinitesimal time dt, and the other one is proportional to the change in the position of the particle following Brownian motion over this infinitesimal period of time. And then we said, okay, so you want an x whose dx is defined by this. Is there a way of producing such an x? Is there such an x? We said, yes, if your coefficients a and b here are not too bad, say continuous, then we can find it. And how did we find this x which satisfies dx equals that? We did Ito integration. And I told you how to find Ito integrals. So we take the period of time from 0 to t, and we chop it, and we compute for each chopping of the period of time a sum, and then we chop time very, very thinly, and then we take the process to the limit, we get something or another, and that's something we are getting. And what we're getting is a stochastic process, a family of random variables indexed by time. What we're getting is a process whose increment from time 0 to time t, so x of t, if you want to know what is x of t, once you fix the universe you're living with, once you fix an omega and big omega, x of t is going to be the initial value of x of 0, plus, well, this expression over here, which we understand very well, it's an integral with respect to time, plus the integral of the coefficient of d Brownian motion with respect to the Brownian motion. And this is what we call the Ito integral. And then we said, okay, if you give me this equation, there is a way for finding an x whose dx looks like that. And we have a name for all the x's whose dx look like that. We call this Ito processes. So the bottom line of all this discussion is, if you tell me that you want, so here, this was an example of computing one of these. If you want an x so that the dx is given by this expression over here, there's a way for me to do that. And the x I construct for you is given by the value of your x at time 0, which you can choose it to be arbitrary, plus these two integrals. So that's a regular integral with respect to time, if you wish, and that's the Ito integral with respect to Brownian motion. So this is what happened in the week before reading week. And now we're going to put this to work, and I'm going to deliver on my promise that I can give you a model for the evolution of prices. But before we do that, let's make sure that you're going to know what I'm talking about. Do we have any questions about what I've just reminded you of? Okay, if there are no questions, let's go back to stock prices. So we want stock prices to jiggle up and down. So here's our first attempt at describing stock prices. We can say, let's have a look at the proportional change of the price of something, so the change in the price divided by the price itself, over an infinitesimal period of time. So here's one way to try to think about this. We're going to say, if you want to know by how many percent your share price changes over an infinitesimal period of time. Well, look at what happens to a particle following Brownian motion over this infinitesimal period of time. Look at the change in the location of that particle, called that dB, the Brownian motion, and multiply this by some constant sigma. So sometimes the particle is going to move like this, and then your price is going to go up. Sometimes the particle is going to move like that, and your price is going to go down. And it's going to be stochastic, and it's going, if you do this for different times, it's going to jiggle up and down. And okay, that's a model. I can say this is what I think prices do in the real world. And you can right away see that this model is doing something good. What is the good thing that this model is doing for us? This model doesn't have any memory. Right? If you look at the change in the position of a particle following Brownian motion over one period of time, and the next period of time, and the next period of time, according to our definition of Brownian motion, these increments are independent of each other, which is a property we want prices to have. We don't want to be able to predict the future by looking at what happened yesterday. Because if we could do that, we would all be very rich. And then the world would change. It would change until no one can predict it anymore. Okay? So that's one property, a desired property of the real world that is captured by this model. So that's one good thing about this model. But now let me show you that this is not a very sensible model. And then we're going to fix it. So why is this not a very sensible model? So I'm showing you here the prices of something. So this is not a single thing. The prices here start from 1920s, and not many things exist all the way from 1920s to now for almost 100 years. So instead what I have here is a collection of things. So that's the Dow Jones Industrial Average. So it's a stock index. It's a price of a basket of shares in the industrial shares in the US. And then you can see what happens to the prices of this basket of shares. And when you look at this growth of the price, it doesn't seem as if it's going nowhere. It looks as if there is some sort of exponential growth with noise on top of it. Notice that if ds over s if it were really true that ds over s is some constant sigma times d Brownian motion, then I can look at so this is this is a random variable and this is a random variable. I can talk about the expected value of both sides. So this would tell me that the expected value of ds over s, the expected value of the change, the proportional change in the price of shares, is the expected value of this. What's the expected value of d Brownian motion? What is dB? What sort of random variable is b of t plus dt minus b of t? Property number 2 of Brownian motion. This is a normally distributed random variable with mean of what? 0. 0. So the expected value of this, which is that, is 0. So this would say, on average, prices are not going anywhere. But we look at this picture, and it doesn't look true that prices are not going anywhere. And if prices were not going anywhere, why would anyone invest in shares? Why not put your money in a savings account? Or what happens to your money? What's your expected return if you put your money under your blanket, under your mattress? 0. So why run any risk? So this picture is telling us that we don't have a very good model. And so we want to fix this. How are we going to fix this? We're going to say, let's change the right-hand side here. So yes, the proportional change in S, in your share price, is this noisy component which jiggles up and down, but then let's add another term to this, which is going to be some constant mu times dt. Okay? And if we look at an S which is defined by this, now what do I mean by that? Let's rewrite this. I can write ds is sigma s, let's write it like this. Mu s dt plus sigma s d Brownian motion. So what did we call this sort of processes? Three letters, starts with an I. That's an eta process, okay? This is an example of an eta process. Hello, can I help you?
Just doing the head counts.
All right, okay. So here's an example of an eta process which has a special name. So when it has this particular form, it's called a geometrical Brownian motion. And now, if we do the same calculation as before, if we ask ourselves, if this is our model for the proportional change in S, what's going to be the expected value of the proportional change in S? So I'm talking about the expected value of this random variable. So it's the expected value of this sum, which is the sum of the expected values. We saw, well, I told you that the expected value of this is 0, and we're left with the expected value of this, which is just mu times dt. So if we now ask ourselves what happens on average over an infinitesimal period of time, then the proportional change is mu times the length of time. So now, what sort of what sort of function behaves like that? So instead of looking at the expected value of this random variable, suppose that I have a function. I'm going to call it f of t. And suppose that I told you that df dt, suppose that I told you that df over f is mu dt. What sort of function behaves like this? This is a separable differential equation if you want. We can solve it, we can integrate both sides. So we're going to get log of f is mu times t plus a constant. And then we take e to the both sides, and then we're going to get f is e to the mu t times e to the c. So let's just write this times another constant, and we know which constant that is going to be. It's going to be f of 0. I hope you've seen things like this before. Does this look familiar to you? Okay. What sort of function do we get then when f, not the expected value of ds over s, not the expected value of df over f, but the actual quantity df over f, if there is no noise in it, if it's not stochastic, if it's not a random variable but just a function, what sort of functions behave like that? What sort of growth do they have? Here's a function of t. What sort of growth does this function have? Exponential growth, because it's an exponential function, right? Okay, so these kind of functions defined by that have exponential growth, and now we can go back to the picture we had here, and we say, the prices which satisfy this condition over here with this term over here, now with this model, they look as if they're going to look a bit like that. They're going to have exponential growth, and on top of this exponential growth, you're going to have some noise coming from Brownian motion. Okay? I have this feeling that over the reading week you forgot everything I told you before. So, and people are saying, yes, we forgot everything you told us before. So, I'd like to help you. If you ask me questions, I'm going to help you. So let me take a step back and remind you what I'm trying to do. I'm trying to describe that. We started by saying, is this going to work? No, that's not going to work because it doesn't explain the exponential growth over that long time. And then we said, let's add this term. And now we have something that, at least in expected values, grows exponentially. And that has a chance of describing that picture. Okay? So, I'm just going to declare now, without further evidence, that this is our model for the evolution of prices. Okay? So soon we're going to look at derivatives, which are going to have, they're going to have prices which depend on the prices of underlying assets. And then we're going to call these prices of the underlying assets S. And we're going to assume, we're going to make an assumption that these underlying asset prices S behave like this, that satisfy this equation defining this ether process S. Okay, so we added this term. Now, on average, we have exponential growth. We're going to give names to the two constants you see here. This constant over here, the mu, the one that controls the exponential growth, is going to be the drift. And this sigma over here is telling you how much noise there is in the price. And we encountered this before. Remember, when we were looking at the prices of call options, we look at two possible underlying assets. So we said we have, this is my time axis, and we started time 0. We had some call option with strike price X, so that's the price axis. We have some call option with strike price X. We observe at this price at time 0, and then we can look at various sort of underlying assets. So we can look at very boring things that don't change very much, and then they never. Your call option with strike price X never expires with a positive price. Or we can have crazy things that look like this, or maybe like that, and these have a chance of breaching the strike price X, and then you can get a positive payoff out of them. And we said the price of European call options should capture this volatility of the underlying asset price, and we gave a name to this volatility of the underlying asset price. We call this the volatility of the underlying asset price. So now, here's where it's being modeled. I'm looking at an underlying asset price S, which behaves like this. If I were to put different numbers here, very small numbers, very big numbers, increasing the sigma increases the contribution of Brownian motion, increases the contribution of this thing that is jiggling up and down all the time, and that's going to increase the volatility of the underlying asset. Okay, so we call mu the drift. This is the term contributing to the exponential growth. And then we have the term with the sigma in it, and the sigma controls the volatility, the variability of the return of this underlying asset. Now let me show you some pictures. So I'm going to show you some instances of a process of this form. And I'm going to fix my mu to be 0.1. So this is fixed to be 0.1. And I'm going to show you pictures of what happens when we take various values of sigma. So the first value of sigma I want to take is sigma is equal to 0. If sigma is equal to 0, what that is saying is that ds, the change in s, is 0.1 times the value of s times dt. So we're back in this case. There is no Brownian motion anymore. And we said, in that case, you're going to get an exponential growth. And we look at what happens in this picture, and we get this nice, smooth exponential growth with no noise whatsoever. And now I'm going to turn up the noise a bit. So I turn up the noise a bit by taking sigma to be 0.05. So now, over an infinitesimal period of time, we have this exponential growth, but on top of that, you have this noisy term. And you can see what happened. We had it looks as if we had this exponential growth, but there is noise on top of it. And now we can increase the volume, and we can take a sigma of 0.1. We double the sigma, and now we get this growth with quite a lot of noise. And then if we take a big sigma, like 0.5, then we get something that you have to think for a moment to. You have to tilt your head a bit to see the exponential growth. There is a lot of noise in it. And this looks a bit more like what we observe in real life. Here, let me show you a picture from real life. Here's the picture from real life. This is the evolution of the price of something which looks like exponential growth with noise in it. By the way, you can read quite a lot of stuff from this picture. What's this? What's this decline in price? So this graph starts in 1920s. So what is that? What is this dip? What happened at the end of 1920s? What happened in 1929? The Great Depression. So here's the Great Depression. It doesn't look that great, right? But that's because you're comparing this to prices which are observed a century after that. But let me show you something a bit more painful, at least maybe not for you, but for your parents perhaps. What's this? What's this? Around 2000 dot-com bubble and crash. What's this? Financial crisis and crash. We are here somewhere. No doubt in 10 years when I teach this course I'm going to talk about the next disaster. And so on. Okay, so right. We have a model for this disastrous growth, which looks a bit exponential. Okay, so that's our model. That's what we're going to use from now on. So from now on, we're going to think of underlying asset prices following this Ito process. This is an Ito process. Okay, let me go back to this a bit later. And the question is this a good model? And the answer is going to be maybe it's good enough, but as in everything in the social sciences, in physics, if you have a good model, then it will predict your measurements with up to 10 digits of precision. In social science, if you have something that predicts the social world, the economics of something, with anything within 20% of the real value, you have a really, really good model. Okay, so our model is pretty good, but it has some problems in it, like all models in the social sciences. So let me show you what I mean by that. So this is again some data coming from the real world, which I collected a long time ago. And what I'm showing you here is some trades in shares in Vodafone a long time ago over 1 minute. Okay. So let's see, how does this fit our model? So it fits it very badly for several reasons. The first reason is that there are trades at discrete times. And prices of things change when there are trades with different prices. Whereas if you write this, there is a change in S for every infinitesimal period of time. So changes in prices in real life are discrete. So there was a change in price as you went from here to here, and there was a change in price as you went from here to there, and so on. And there was no change in price in between those times. If you adopt this model, things are changing all the time. Things are jiggling all the time. So that's one thing that your model seems to be getting wrong. Another interesting thing about this, what sort of numbers can this S random variables take? Any real number, or at least any positive real number. But you see here that there is some unit, smallest unit of price, which is about 1/1000th of 1 pence. So in real life, prices are discrete too, unlike in our model, but that's not a big problem. Let me show you a bigger problem. So there are two prices. So whenever you go to a market of everything, you're going to observe two prices. And maybe I'll tell you why one day. So there is a bid price and an ask price. The bid price is what you get if you sell something to the market, and there is an ask price, which is what you pay to the market if you buy something. Now, if you look at these two prices, the gap between them is more or less constant. And then the actual prices which are charged in the market for various things are somewhere in between most of the time. So if we look at prices now, so this is time, this is price. There are two prices. So there is the price that you pay to buy things, and there is the price that you get for selling things. And if they look like that, it would be okay, because you can say, okay, the gap is about the same, more or less. So if I just knew what is this price, I would be able to know what the other price is. And this is true in boring times, but in interesting times, interesting things happen. So if suddenly now some airplane crashes into a tall building, you're going to see something like this. People are afraid, they don't want to run any risk. They say, if you're going to sell me these shares, I'm going to pay you very little. If you want to buy them from me, I'm going to charge you a lot. And why is that? Because these people buying and selling have to keep an inventory of shares, and in these uncertain times, causes them some risk. And we are not going to model this. We're not going to model this widening and narrowing of bid and ask prices. So that's another thing. If you really want to describe the world, and to describe the world, you have to describe interesting times, not just the boring times, then you have to model two prices. And we're not going to do that. Okay, so let me repeat myself. That in the real world, there's a smallest unit of change in price, and the price changes not continuously, but discretely, and there are bid prices and ask prices. We're going to model only one of these, one price. We're going to pretend that there's only one price. And the more serious problem with the model is what before I praised as a good property of the model, which is this. Normally, in normal times, prices have no memory. Now let's go and live in some interesting times. So here's boring, 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 boring. Then something happens. I don't know, World War III starts, and then this happens. Okay, so that's 1 second after the beginning of World War III. What do you think is going to happen next? Boring, boring, boring? No. People are still panicking, right? So if something really bad is happening and prices have gone down a lot, and you have to bet whether or not prices are going to go down during the next second or so, it's a safe bet to bet that they're going to go down. They're going to go down and down and down until they find some support, and maybe they're going to look like this. Okay, so if you're in the middle of the crash, if you're falling off a tall building, and you ask yourself, what's going to happen during my next nanosecond, you're still going to be falling, okay? You're not going to start going up suddenly. And we are not going to model this. We're going to assume if you just observe this collapse and you ask yourself what's going to happen next, then our model is going to say, I don't know, maybe you're going to go up, maybe you're going to go down. So we're not going to model the more interesting bits of history. So we're going to take our model and we're going to treat it as an approximation of what happens in real life, an approximation that leaves out the more interesting moments in our lives. Okay, but now that I told you why this is not such a great model, we're going to declare it our model and we're going to use it from now on. So what do we want to do with this model? We want to use it for something. What do we want to use it for? We want to use it to find prices of derivatives. And how are we going to do that? We're going to say the price of a derivative is going to be some function, some mysterious function of the price of the underlying asset. Okay? So we're going to take the underlying asset price, which is this complicated thing, jiggling up and down. We're going to look at the function of that this collection of random variables, and that's going to model the prices of our derivatives. So to do that, we need to be able to describe functions of eta processes. So here's an eta process, what we declare to be an eta process. So it's a stochastic process X, which is defined by saying what dx is, what is the infinitesimal change of x over an infinitesimal period of time. And there's two components, as we said before. There is a component which is proportional to dt, to the change in time, and a component which is proportional to the change in the position of a particle following Brownian motion. And now we say, okay, let's look at a function of x and time. What is that? How do we describe that new process? If x is a collection of random variables indexed by time, in other words, a stochastic process, I can take a function of two variables, and I can plug in this x into the first variable and time into the second, and I can give this a name. I can call this y of t. This is a new family of random variables indexed by time. So suppose that I know that this is an eta process, it has that form. What do I know about this new family of random variables indexed by time? What do I know about this stochastic process? Okay? So this is what we want to do next. And it has a name. So I'm repeating myself. So I take y to be a function which I call g. Let's change this to match what you see in the slide. You take y to be a stochastic process which is defined as a function g of the stochastic process x and time. And then you ask yourself, if you start with the stochastic process x, which is an eta process, what is y? And the answer is given by Ito's lemma. Ito's lemma is saying, if this function g is not too bad, so it has to be twice continuous differentiable with respect to the first variable and continuously differentiable with respect to the second variable, which means that it has a continuous second derivative with respect to x and a continuous derivative with respect to t, partial derivative with respect to t. So if g is not too bad, then y is also an eta process. Aha, what does that mean? What sort of a statement am I making when I say y is also an eta process? What is an eta process? To say that y is an eta process means that the change in y, dy, has two components. One of them is proportional to dt, to the infinitesimal period of time over which we're computing dy, plus another component which is proportional to what we call dB, the change in the position of a particle following Brownian motion over this infinitesimal period of time. So to say that y is an eta process means that the change in y has this form. And this is what Ito's lemma is saying, and it's saying not only am I going to show you, or Ito is going to show you, that this y defined by this function of the eta process x in time is an eta process, it will tell you what are the coefficients here. So what are the coefficients there? Here they are. So what is this saying? This is saying take your function g, compute the first derivative with respect to the first variable, evaluate this at x and t, capital X and t, multiply this by a, which is a function of x and t as well. So here's this quantity here, and then take your function g, find its derivative with respect to t, plug in big X and your t, and so on. So that's going to be the coefficient of dt. So this is what goes in here. And what goes in here, well, let me write this with all the details so that we don't get confused by this. So you take your function, which is a function of little x and little t. You find the derivative of this with respect to the first variable, little x. You evaluate this at x, the stochastic process x, and t, so the value of x times t and t. And then you take b, which comes from here, up here, and you multiply it by that. So this term over here looks like this. This bit over here, eta says, is equal to that. And similarly, you can fill in the details in here. Okay. So I promised you that this material is not simple. And this is about the end of our technical suffering here. Once we know this, we can roll up our sleeves more or less, and we are going to start finding prices of derivatives. So let's make sure that we understand this technical bit over here. So I start with an eta process. So there is a stochastic process x, which has the property that dx, the change in x, is a dt. So a is a function of x and t, dt, plus b, which is a function of x and t, the Brownian motion. And then we look at y, which is a function of this process x in time. And I ask you, what sort of process is y? It's a process which is defined by this. The change in y, the infinitesimal change in y, is that expression times dt plus this expression times db. Okay? Do you understand what this theorem is saying? Okay, the proof of this is a bit intricate, and we have to do things a bit more carefully for us to produce a proof, but I'm going to give you some good arguments why this should be true. And at the heart of that argument is that very strange statement. So what I'm going to write now is very imprecise, and I'm going to wave my hands. So don't take this as a proof for anything. I'm going to wave my hands, and I'm going to convince you that whenever you see the square of d Brownian motion, you can replace this with dt. Notice that I put this in inverted commas, because I need to work much harder than that in order to make this into a meaningful statement. So you take the change in the position of the particle following Brownian motion over an infinitesimal period of time dt, you take the square of that, and you're going to get the infinitesimal period of time dt. Now, let's see if I can convince you that this is making sense. So how do I convince you that this is making sense? Instead of taking the infinitesimal period of time dt, let's take a short period of time, delta t. And if I do that, what is going to be dB, the change in the position of a particle following Brownian motion? It's going to be the position at the end of this time period minus the position at the beginning of this time period. Okay? What sort of thing is this? Say it so that I can hear. It's a 0. If this was 0, this would be saying that the particle following Brownian motion from this point in time to this point in time doesn't go anywhere. It stays where it is. What sort of creature is this? Is this a mammal? Is this a plant? Is this a number? Is this a person? What sort of creature is this? I fix t, say tomorrow. What is b of tomorrow? A? Say it so that I can hear. A random variable. Okay. And what is this? B at tomorrow plus a minute. It's a random variable. And this difference is a random variable. And property 2 of Brownian motion says this difference is what? Look at property number 2 of Brownian motion, and you're going to discover that it says that this is, it starts with an n. Normally distributed with mean 0 and variance equal to the length of this time period, delta t. Right? Yes? Okay, so this difference is normally distributed with a variance of delta t. So I can take a standard normal random variable z and multiply it by the square root of delta t, and what I end up with is exactly this difference. It's normally distributed with mean 0 and a variance of the square root of delta t, which is delta t. Okay, so now let's calculate the variance of z. It's 1 because it's a standard normal random variable. On the other hand, I can compute what this is. It's the expected value of z squared minus the square of the expected value, and the expected value of z is 0. Why? Because it's standard. And then I get that the expected value of z squared is 1. Okay. Now let's see if this helps us for anything. So let's ask ourselves, here's another random variable, the square of d Brownian motion. What's the expected value of that? Okay, so the expected value of that is, well, let's see, dB was written in this form, the square of that is here, and then I can pull out the delta t outside, I'm left with delta t times e of z squared. Z squared, I convince you, is